Good morning. We continue our course on formal language and pattern codes. Today we have a very short lecture which will be devoted to the following two elementary question about for regular languages. We now come to a very fundamental issue. Given a language L and a string W, can we determine whether or not W is an element of the language L? This is a membership question and a method for answering. It is called a membership algorithm. We shall make precise that the term algorithm means for the moment, think if it is a method for which we can write a computer program. Very little can be done with languages for which we cannot find efficient membership algorithms. The question of the existence and nature of the membership algorithm will be a great concern in later discussions. It is an issue that is often difficult. For regular languages, thought it is an easy matter. We first consider what exactly we mean when we say given a language. So in many arguments, it is important that this be ambiguous. We have used several ways of describing regular languages: informal verbal description, thesis notation, finite automata, regular expressions, and regular grammars. Only the last three are sufficiently well defined for use in theorems. We therefore say that a regular language is given in a standard representation if and only if it is described by a finite automaton, a regular expression, or a regular grammar. Theorem. Even a standard representation of any regular language L on alphabets sigma capital and any word from the sigma star. There is an algorithm for determining whether or not the word W is in the language L. The proof. We represent the language by some deterministic finite acceptor, then test W to see if it is accepted by this automaton. This is complete. Proof. Other important questions are whether a language is finite or infinite, whether two languages are the same, and whether one language is a subset of another. For regular languages, at least, these questions are easily answered. Theorem. There exists an algorithm for determining whether a regular language given in a standard representation is empty, finite, or infinite. Proof. The answer is apparent if the represented the language as a transition graph of the deterministic finite acceptor. If there exists a simple path from the initial vertex to any final vertex, then the language is not empty. To determine whether or not a language is infinite, find all vertices and that are the base of some cycle. If any of these are on the path from the initial to a final vertex, the language is infinite. Otherwise, it is finite. This completes the proof. The question of the equality of two languages is also an important practical issue. Often several definitions of a programming language exist, and we need to know whether, in spite of their different appearances, they specify the same language. This is generally a difficult problem. Even for regular languages, the argument is not obvious. It is not possible to agree on the sentence-by-sentence comparison. We call this work only for finite languages. Nor is it easy to see the answer by looking at the regular expression, grammars, or deterministic finite acceptors. An elegant solution uses the already established closure properties. Theorem. Given standard representation of two regular languages, L capital 1 and L capital 2, there exists an algorithm to determine whether or not L capital 1 is equal L capital 2. The proof. Using L capital 1 and L capital 2, we define the language L capital 3, which is equal the union of the following sets: L capital 1 intersect with the complement of L capital 2, and the union with the complement of L capital 1 intersection with L capital 2. By closure, the language L capital 3 is regular, and we can find a deterministic finite acceptor M capital that accepts the language L capital 3. Once we have M capital, we can then use the algorithm in theorem 4.6 to determine if the language L capital 3 is empty, but that L capital 3 is empty if and only if L capital 1 coincide with L capital 2. This completes the proof. This result is fundamental in spite of being obvious and unsurprising. For regular languages, the questions raised by theorems 4.5 to 4.7 can be answered easily, but this is not always the case when they deal with the other language families. We shall encounter questions like these on several occasions later on. Anticipating a little, we shall see that the answer become increasingly more difficult and eventually impossible to find. So thank you for your attention. I finish my lecture. I wish you good luck. Finish the war. Goodbye.